Hey everyone, and welcome. Today, we're going to talk about one of the most fundamental forces in the entire universe, gravity. We're going to be looking at the gravitational field, that, invisible influence that tells planets how to orbit, stars how to form, and even why an apple falls from a tree. It's like the silent architect of our cosmos, and today, we're going to decode its secrets.
All right, let's just jump right in with a classic puzzle. Imagine an astronaut on the moon. They're obviously the same person, right? The same amount of stuff makes them who they are. But we've all seen the videos. They feel super light, they can bounce around like it's nothing. So what's going on here? The answer gets right to the heart of what we're talking about today.
To get to the bottom of that astronaut puzzle, we've got to get crystal clear on two words we mix up all the time in daily life: mass and weight. In physics, they are totally different things, and that difference is everything.
So first up, you've got mass. The easiest way to think about mass is that it's just the amount of stuff inside an object. It's a fundamental property. So whether you're right here on Earth, you're on the moon, or you're floating out in deep space, your mass, measured in kilograms, never ever changes. It's the constant U.
Now weight is a whole different ballgame. Weight isn't the stuff you're made of. Weight is a force. It's the force of gravity pulling down on your mass. And because it depends on gravity, your weight, which we measure in newtons, can change big time depending on where you are.
So this table really breaks it down for us. Mass is constant. Weight, that depends entirely on where you are. It's a variable force you calculate by taking your mass and multiplying it by the local gravitational strength, which we call g.
So let's get back to our astronaut. Let's say they have a mass of 60 kilograms. Well, here on Earth, where gravity's pretty strong, their weight is about 600 newtons. But take them to the moon, where the gravitational pull is only about 1/6 of Earth's, and their weight plummets to just 100 newtons. Same person, same mass, but a completely different weight. And just like that, puzzle solved.
Okay, so weight is a force from a gravitational pull. But how does a planet actually pull on something without touching it? I mean, there's no rope connecting you to the Earth, right? Well, physicists came up with this incredible idea of an invisible field. And this is a really powerful way to think about it. Instead of some kind of mysterious action at a distance, we just imagine that a huge object, like a planet, actually warps the space around it. It creates this gravitational field. Then, any other object with mass that enters this field feels a force. The field is the thing that connects them.
And we can actually measure how intense this field is. We call it the gravitational field strength, or G. It's basically the force that every kilogram of mass would feel at that point. Here on Earth's surface, it's about 9.81 newtons for every kilogram. And that number might sound familiar. It's also the acceleration of free fall, 9.81 meters per second squared. They're really two sides of the very same coin.
Now here's where it gets really cool. All of this behavior, from a simple apple falling to an entire planet in orbit, can be described by one single, beautiful equation. It's like gravity's master code. And here it is. The gravitational field strength, G, is equal to big G, that's the universal gravitational constant, it's the same everywhere, times the mass m of the big objects creating the field, all divided by the square of the distance r from the object's center. With this one formula, we can figure out the strength of gravity basically anywhere.
Now that r squared on the bottom is super important. This is what we call the inverse square law. It means that gravity gets weaker not just with distance, but with the square of the distance. So it drops off really, really fast as you move away from something. All right, let's put this powerful formula to the test. I mean, theory is great, but seeing it in action is where you really get a feel for it. We're going to use it to do some pretty amazing cosmic calculations, starting right here at home with the Earth-Moon system. Our source material has the perfect worked example for this. We've got all the data we need right here, so let's use it to uncover some secrets about our own planet.
So, first up, a monumental challenge. How in the world do you weigh an entire planet? It's not like you can just pop it on a bathroom scale, right?
Well, check this out. We just take our master formula and do a little algebra to solve it for mass, or m. Then we can plug in the numbers we already know, the Earth's radius and the gravity we feel right here on the surface. And with a little math, we can figure it out. And the result is just mind-blowing. It's almost 6 times 10 to the 24th kilograms. That's a 6 with 24 zeros after it. We just weighed a planet without even leaving our chair. How cool is that? Okay, so now that we know how massive the Earth is, let's see just how much weaker its pull gets by the time you're all the way out where the Moon orbits.
We use the exact same formula, only this time we plug in the Moon's orbital distance for r and that giant mass for the Earth we just found. And you can see the field strength just plummets to this tiny, tiny fraction of what it is on the surface. But is a pull that small really enough to hold on to something as huge as the Moon?
Let's find out. To get the total force, we actually have to consider the mass of both the Earth and the mass of the Moon.
For this, we use the full-on version of Newton's law of universal gravitation, which, as you can see, includes both masses, big M for Earth and little m for the Moon. And the force turns out to be 2 × 10⁻20 newtons. That is an absolutely immense, invisible tether holding our Moon in its perfect orbit, stretching across hundreds of thousands of kilometers of empty space. Incredible!
Okay, we've totally dissected the Earth-Moon system. Now, to really make sure this knowledge sticks, let's take our formula on a little trip to the king of the solar system, the gas giant Jupiter.
So here's our challenge. What's the gravitational field strength at the surface of Jupiter, given its huge mass and its radius?
You know the drill by now. The process is exactly the same. We take our trusty formula and we just plug in the values for the gas giant.
And the answer works out to about 25 newtons per kilogram. Now remember, Earth's is 9.81. This means you would weigh roughly 2.5 times more on Jupiter than you do right here. You'd feel incredibly heavy.
All right, we have covered a ton of ground. Before we finish up, let's do a quick-fire review of the biggest ideas to make sure they're locked in. First, what was that master formula, the key to this whole thing?
That's the one. G equals gm over r squared. That little equation lets you calculate the strength of gravity anywhere in the universe. Second, how does that field strength change when you move farther away?
Yep, it follows that inverse square law. It gets weaker really, really fast. Double your distance, and the force is only 1/4 as strong.
And finally, let's bring it all back to weight. If you know an object's mass and the local field strength, how do you find the force on it?
It's super simple, right? You just multiply the mass by the local field strength g. So a 500 kilogram satellite in a field of 8 would feel a force or weight of 4,000 newtons. Easy as that.
So the crucial point in all of this, the big takeaway, is just how powerful one simple formula can be. Think about it. From something as basic as dropping a ball, to calculating the mass of an entire planet, to understanding the forces holding our Moon in orbit, it's all described by the same elegant piece of physics.
And I'll leave you with one final thought to really chew on. That formula, G equals gm over r squared, shows that the field strength only becomes 0 when the distance r is infinite. That means every single object with mass, and that includes you, creates its own gravitational field that stretches out across the entire universe. Your influence, however tiny, is literally cosmic.